Now let's go back to the leakage problem, right? The problem is if I don't evaluate, if I evaluate this is 0, I need to keep this at VDD. But during the evaluation, this is not static logic. Remember what is static logic? The output always has a low resistive path connecting the output to either VDD or ground. During evaluation, clock is off. And this is on. However, let's say the input is 0, then this is off. This is floating, okay? Floating doesn't look like a bad stuff, but the problem is the charge can leak away. So here show you that what happened. When this is at pre-charge, no problem. The output pre-charge too high. But then when you are in evaluation, even the output supposed to high is dropping, is leaking the charge. The charge is leaking away. Why it is leaking away? Here show you 4 paths, okay? The best way is just to do the layout and recall what we learned before, okay? So I have the output here, right? Let's say this is the P substrate. This is the N plus, okay? And then this, of course, is M1. So this is A equal to 0. And then maybe this one goes to the ground. Let's say it goes to the ground through the ME, right? And I also have a PMOS, P plus, and then have N. Of course, I need to connect the N well to VDD. Okay, this is the clock. And this one is connected to this one to the CL, right? Because this is the drain, this is a drain, okay? And just now you already helped me to set the stage. This one is P plus, we connect to VDD. Connect to ground, right? This is connected to the well, and here connect to the VDD. Now let's look at this path. N is at VDD. This is at P. Okay, so the good thing is, first of all, even this is turned off, I have number 4, leakage. Number 4 basically is a leakage. It helped me to charge up the output. So this is good, right? Because I have VDD here, if I keep leaking away the charge, this one will help me to charge up the output to CL. But on the other hand, I also have this one connected to, and and at the same time, this diode connected to the N well, and this one form a diode. This is path 3. This is also good in this case. It helped me to charge up the CL, right? Because it's reverse diode. So you charge up the CL. But the problem is 1 and 2. Look at this. Here, this is at VDD, right? We assume this is at VDD. This one and this one form a reverse leakage diode. Okay, and this is path 1, right? The charge will try to leak away if you stay a long time during the evaluation. And at the same time, of course, I also have the leakage, right? This is the leakage of the MOSFET. It will try to leak away also because this is ground, right? So there's a competition. All you need to know is that there's a competition. There are so many paths. And if you don't do it well during evaluation, I will lose the charge. Then my data will be gone because I expect this to be 1. Eventually, we will drop to 0. Then it's a wrong logic. Is this okay? Any questions? Right, so this is one thing. So if that is the case, what can we do? We try to add something called bleeder transistor. This is the bleeder transistor, right? So what we do is we try to add another NMOS, another PMOS to charge this up. For example, if this output is VDD, then you will make this one to be 0. Then you will turn this on, right? So this will keep charging up this output if the output is supposed to be high, even there is the input, there is leakage. And it's very obvious what is the drawback of adding this setup to avoid leakage. Anyone has an idea? What's the drawback of adding something?
It takes up more area.
Area.
Consumption.
And power consumption. Very good. Right? It's as simple as this. Do not forget, this is also an area. You need an inverter. Okay. But however, this one should not be too wide, right? So that we can switch. Right? So if you are too strong, then I evaluate this one. This time I really want to discharge, but you're too strong. I can never discharge it. So this one cannot be too strong, which is good, right? If it's not too strong, that means we can have a smaller area. So you need this when you have a long evaluation cycle, but then you need to also think about area and whatever. So this is one possible solution. Okay. Any questions? Now, another is what you just told me, charge sharing. What is the problem? This is during evaluation. Right, during evaluation, this is off, this is on, okay? And then let's say it happened that the input B is 0, so this is off. Then what does it mean? It means that the output has to be high, right? This is our goal, but we have internal capacitor. A is high in this case. Output should still be high, but there will be charge sharing, okay? So there are two cases. The case one is that the charge just share between them while MA is on, right? So it means what? At the beginning, I have VDD times C out. That is the total charge, right? But after sharing, it becomes Vx. C out times Vx plus Ca times Vx, right? Because after charge sharing, they becomes the same potential if MA is always on, right? So the total charge is constant. As a result, the C out, but I forgot one thing, sorry. Sorry. And then of course, Vx, which is just V out, right? Now it is what? It's just equal to C out divided by C out plus Ca times VDD. Smaller than VDD. So that is the problem of charge sharing. That is one thing. Okay, if you have a large Ca, if it's 0, then it is just VDD, right? If you have a large Ca, then you will have a very small V out. It's no longer VDD. Okay. Case 2. It is possible that when you charge up, this one go higher and higher and eventually turn off this transistor because this one cannot be more than VDD minus VTH. So it stopped at VDD minus VTH. Is off when Vx equal to VDD minus VTH. Okay, so in this case, it means that then you don't have charge sharing anymore, right? But it definitely tells us that the total charge VDD original that I have is equal to Cx times VDD minus VTH. Maybe let me write the whole equation. It equal to Vx times Cx, then plus V out times C out. Okay, let me say this is C out. Okay, right? Then of course we say Vx equal to VDD minus VTH, right? So this is VDD minus VTH times plus V out, C out. Okay, so in summary, you just do some shuffling of the terms. You see that V out equal to C out VDD minus CA times VDD minus VTH divided by C out. Anyway, just to tell you that there are two cases. When you do it, you need to be careful. But the point is that the output is always less than the VDD, right? Because of the charge sharing. The rest are just math. Is this okay? Any questions? Now, how do we solve this problem? You already gave me, right? But we want to pre-charge it. Again, add a breathing transistor to charge the internal node. Now you see that dynamic logic is really not good. It was very useful in the past when we need very high-speed circuit and when the integration is not large. But now it is not as good as CMOS, static logic, right? So what we do is when we are charging up the during the pre-charge phase, besides charging up this node, we also charge up the internal node. And no need to say, right? What's the problem? You increase the area. And not just the area, right? You actually will be slower because now CA is larger. Can someone tell me why CA is larger now? This is CA.
Because we are increasing the size of the NMOS transistor.
NMOS will still the same size. But what else do you see at this node?
Do we also see the drain capacitance from BL? Yes,
because also see the drain capacitance of MBL, right? So you now that you do have the gate drain capacitance here, right? You can, or you did not draw it, but whenever you connect one transistor to another, you immediately know that it's not that simple. You are adding an extra capacitance to me. Okay. Now then there's another problem called clock feed-through, which is not that difficult to understand, but is also very important, right? Let's imagine that we have this circuit again.
Professor?
Yeah.
So how do we implement transmission gate using dynamic logic?
How do we what?
Transmission gate.
Transmission gate, we don't have dynamic logic, but transmission gate itself is another kind of logic, right? Mm-hmm. So you use transmission gate to implement multiplexer or whatever. Transmission gate is you want to transmit directly the signal from the source to drain instead through the.
Yes.
Yeah, I cannot say that, but I mean, of course you can couple them, but I don't know. You know, if you can do transmission gate with the static logic, then you do the same thing with the dynamic logic. That's what I'm trying to say. They are not exclusive, or I don't know if I answer your question.
No, it has some PMOS logic, right? So in the transmission gate. So do we need to get rid of that PMOS logic and implement NMOS?
No, there's no such version, right? Because transmission gate, you go ahead with this PMOS and NMOS together. If you remove this PMOS, then you have other problem. We are going to talk about transmission gate later.
Okay.
The
Yeah, so I have one more thing. So how do we design the clock for the dynamic logic? Like what are the parameters that need to be considered for the clock design?
The clock, I think the most important is the delay, because you need to drive so many PMOS. So you have a constraint. First of all, what is the frequency you want to achieve? And then now you need to look at all these PMOS. How are they going to slow you down? You see what I mean? It's not, you cannot just optimize locally, because the single clock is driving so many gates.
Let's say the pre-charge and as well as evaluation period, right? So that is dependent on the number of gates, like the periods of these gates.
Number of gates, again, right? What I say is this: the clock is driving many logic gates, so the delay, right? What clock cycle you can have depends on how fast you can drive the clock in the whole circuit block. It's not just the single gate. Here is one gate, here is another gate. You see what I mean?
Yeah, I got it. So is there any formula or any other thing where we can consider this equation so that we can design the clock, or is it like a random?
Not random. You just go back to what you learned, right? RC delay. How much time you need to drive, or how much time you need to propagate the signal. This is a transmission line, right? You just go back to what is the capacitance of your clock, and then resistance, and then how many gate capacitance you need to drive, and then calculate it, and it need to be smaller than the half of the period.
So Professor, in case of the hand calculations, we can do for 1 or 2 transistors, but whenever
okay,
we
let me
deal
ask
with
you, are you asking about exam or asking a real design?
a real design, let's say if we have
Real
some
design, then
thousands
that is what you need to do. Yeah. Oh, then real design first. This is some first order calculation. Yeah, you don't use hand calculation. You write a MATLAB program, or you then use the computer aided design to design for you, to find out what is the maximum delay, right? Even for this logic, you don't, even for what I'm teaching you here, you don't use hand. You actually just have an estimation and then use the EDA to help you.
Okay, got it.
So the problem in that, right, the feedthrough, let me talk about the feedthrough. The feedthrough, for example, if now, let's say this is a LAN gate, this is 0, this is 0, right? So during evaluation, this is VDD, okay? Now, during the, first of all, you charge up, and this is off. This is the pre-charge state, okay? And what happened after that? You want to evaluate, right? So when you evaluate, this one is on because this one turn on, and then this one turn off. Right? This was off, but this was on, right? 1, 1, 1. And at this state, this is at VDD, correct? And when doing evaluation, this one becomes off, on, because this one go up. But this one is going to change because this is floating. We have a capacitance CGS here, right? So think about a capacitor here, CGS. At the beginning, this is 0 volt. This is VDD. Let me change the color again. Right. It was 0 at 1, and then become VDD at 2, right? This is a floating, it is floating. So this becomes, oh no, this is also 1. Then this one become VDD. What happened to this one? Can someone tell me? What happened to this one? When it was difference was VDD, it means C times VDD equal, let me make it specific, right? VDD minus 0 equal to Q. When you're switching, Q doesn't change. You cannot move the charge immediately. So good. As a result, it becomes 2 VDD minus VDD, right? Because charge is constant. This is an extreme case. Of course, we actually can have other divider effect. I did not take this into account. But this is called clock feed-through. It was VDD, and then now I make it larger than VDD. Well, what is the problem? Larger than VDD isn't that is great, because I have larger than VDD, then it's 1, right? But life is not that simple. When this is larger than VDD, remember what we say about this one? This is PMOS. And now you make this from VDD to 2 VDD or larger than VDD. How do we bias the well? The well is at VDD. You forward bias. Then what will happen? You lose the charge, right? Because you are at VDD, then it will go down to VDD, okay? But the problem is, this is not VDD because this is not completely floating. Eventually, this will go to less than VDD because we have a capacitor dividing effect. This is just a transient, right? So without leakage, you go to VDD and then go back to VDD gradually. But because of this leakage, you actually lose the charge. So eventually you will lose the logic. So it's no longer high. Is this okay? And what is the problem of dynamic logic? Another problem is we want to cascade it, right? So I want to propagate this signal to the next signal. Let's look at this. When the input is high, that is good, right? High, what does it mean? I want it to be low. So this is high, okay? But the problem is this: during the evaluation, during the pre-charge, this is pre-charge. The output the output is evaluated to high, right? This part is high. As a result, once we go to evaluation, then I will start discharging the output. That is because it takes time for me to go to, this one was high. It go from high to 0, right? To 0, right? So when I'm evaluating this one, the next stage, this one input still see high, so it start discharging. But actually, my evaluation should give me 0 because this is high. But it takes time to realize that this should be 0. It takes so much time to be 0, right? And then, but the output already discharged to some extent. This is like the glitching effect, but not recoverable. Any question regarding this? Okay, so if this is the case, what can we do? We can use something called domino logic. We always make an inverter to here. Okay, so by doing inverter, what do we do when we pre-charge? We pre-charge to VDD, but actually this is 0. So we avoid any turning on of the next stage. So if it is 0, then we don't turn it on. It won't affect the last next stage. But if you turn out this one supposed to be 0, then this will go up to 1. then it will evaluate. So you don't have the problem. The problem here is because you're supposed to give 0 to the next stage, but you start with 1. So you start evaluating wrong in the next stage already. By adding an inverter, then you don't have this problem. Right? Here, we'll do this. You always start from 0 during evaluation. Okay. But if you do this, only non-inverting logic can be built because this is non-inverting. We add an inverter. Okay. So what else can we do? We can use so-called NP domino. Well, if the evaluate one causing this early discharge problem, if I fit this to a pull-up network, so these are two different types of domino. Here I have the pull-down network, and then with the clock here, this is the P-type. I use the pull-up network, but I use the discharge. The pre-charge is at here, and then this is the evaluation. By using this method, then I can avoid that problem, and I don't need an extra inverter unless I want to connect it directly to the end block. Any questions? Maybe I go a little bit fast. But that's it, all what I want to talk about for this new material, which won't include in the midterm too. Maybe let's just go to the first thing. I say homework, but let me start with the review.